Sometimes when we're controlling our motors, we want to know things like how fast are they going, or how far have they moved, or how far have they rotated, and things like that. For brushed DC motors, that is particularly challenging because depending on the amount of voltage, current, and the load of the system that we're putting in, we're going to get different rotation rates. For brushless and for stepper motors, we have a little bit more control over their how fast they rotate by controlling the fields of their internal coils, but we still might not know if, for example, we've overloaded or we've ticked over extra because we're being driven by the outside or drifting or something like that. And this is where encoders come in. And what an encoder is principally we're going to be talking about rotary encoders, and basically it's a way of monitoring the speed or position of a rotating joint of some kind, a rotating interaction, right? And the way that most of these work is we have some kind of disk and we have a light source and a photosensor, and they can be either reflective or they can be pass-through. In this case, we have a pass-through type of thing where I've got a bunch of slots cut in this disk, or it's a transparent disk with with dark bands painted on them. And as the disk rotates, the LED is seen basically being occluded and then revealed by the photosensor. So we'll see spikes in the brightness of light as it goes through this disk, and by counting those spikes we can see whether or not the disk is rotating or not. This is a quadrature encoder that uses two sensors, and by using two sensors that are slightly offset from each other, we can figure out if the motor is turning not only how far the motor has turned, but if the motor is turning clockwise, if one channel is leading the other channel, or if it's turning anti-clockwise, the other channel would be leading the first one, right? So we can detect both direction and distance of how far the motor has traveled, the angular distance that the motor has traveled. Absolute encoders work in a very similar way technically, but they're a lot more complicated. And the idea here is, instead of just a regular pattern of stripes, we have 8 different bands of stripes. So I've got one band here. You can see it goes halfway through the entire rotation. This one goes a quarter of the way. This one goes an eighth of the way, a 16th, a 32nd, so on and so forth. And you get my drift, right? So this is a 8-bit rotary absolute encoder, and for every location on this rotary encoder, we can basically interpret it as a binary pattern. So for this particular location, we get a binary pattern of 0 is the dark part, 1 is the light part, dark, dark, light, light, dark, right? And you can see that this, in binary, this is location 102 on the disk. Now, I've got 8 bits here. That's 256 regions on the disk, 360 degrees all the way around the disk. So if I'm at position 102, I multiply it by 360, divide the number of regions I have on the disk, and I'm at my position of 143.4 degrees. And the idea here is that these absolute encoders are used when we need to know the exact position of the motor at any given point. So these absolute encoders are used in things that don't rotate all the way around very often, so things like the joints of robot arms, or in heavy machinery, or things like that. There's a couple of different technologies for encoders. The most common is optical encoders. These are also the cheapest because they're the easiest to make. They're not terribly precise because of the nature of optical systems, but we can make them work for most situations. We also have Hall effect sensors, which are more reliable, particularly in dusty or dirty environments where the disk might get the disk of an optical encoder might get gummed up or grossed out by environmental conditions. So these Hall effect sensors sense the passage of magnets on a disk. So we put a bunch of magnets on whatever is rotating, and as the magnets pass, they cause a square signal to be generated in these very inexpensive sensors. So these are very environmentally tolerant, but we don't get a whole lot of resolution because it's really hard to cram a whole lot of magnets onto one wheel or disk very often. And the last type is capacitive. These are the most expensive to make, but they can be the most precise because we're actually using an analog signal from these things. So we can get a very precise analog representation of rotation as two plates move past each other as they rotate for these capacitive sensors. They are also tolerant to environmental conditions, so they work really, really well, but again, they're expensive, very expensive to make because they require very precise manufacturing to get a very precise, basically variable capacitor to operate reliably over the course of the rotation. Servos are a particular awesome combination of a motor, a control circuit, and some kind of position sensor. Often it's a very cheap potentiometer or variable resistor, which is another technology we can use to measure position. This is an analog version, and because the potentiometer isn't able to rotate all the way around, often servos are only controlled from a very limited range, about 180 degrees of rotation, but they're very handy because they're all of this control system, motor, and feedback system built into one thing, and they come in a bunch of standard sizes. So you might have mini or micro servos. This is a standard size servo. That's the jumbo size servo. They're used so much in things like hobby airplanes and remote controlled cars that they've been greatly standardized and are swap outable. You can get all kinds of versions and all kinds of different sizes and strengths. The way these things work is that they take a PWM signal at 50 hertz. So the period of the PWM signal is at 50 hertz, and the pulse width between 1 millisecond and 2 milliseconds defines the position that the little control board will force the horn, which is the rotating part, to move to. They're electrically super simple. White is the PWM signal, and red and black on the connector is power and ground. They typically take between 4 and 6 volts. 5.5 is the sweet spot, so we have to manage those voltages, but otherwise they're really simple to control and very handy, and you'll be actually using one of these in your robotics project for this semester.